Hi, it's Mr. Anderson, and today I'm going to talk about energy, work, and power. Now, what is something that has energy? It's a pretty big term. So what things have energy? Well, we would say something in motion or something due to its position. We could say that electricity is a form of energy. We could say that matter can contain energy within its chemical bonds, or light has energy, or sound has energy. So that's a lot of different things. What is energy? Energy, therefore, is the ability to do work. Well, that's one of those definitions that requires us to dig a little bit deeper. What is work? Work in science is simply a force times a distance. So anything that can apply a force over a given distance is said to contain energy. And we measure that in joules. So work is measured in joules. And so let's give an example. Let's say, for example, that you want to take a can of Coke and you want to carry it to the top of a set of stairs. Well, that can of Coke has 4.0 newtons of weight, and let's say that you have to climb up a set of stairs that is 3.0 meters high. Now, the interesting thing is that since the gravitational force is always acting down, it doesn't matter if you get to the top of the stairs by walking upstairs, or get to a similar distance by climbing up a ladder, or simply just throwing the can of Coke up to that point. If you've moved it up a certain amount of distance, we'll call that 3.0 meters, then you've done 4.0 newtons times 3.0 meters, or 12 joules of work to get that to the top. Now, you could get that to the top in a couple of different ways. Let's say that we were to gradually make our way to the top of the stairs, or we were to run up the stairs. Well, we would be doing the same amount of work depending on if we're running or going slowly. And so we need another term to figure out how fast we're doing that, and that's called power. And so power is defined as the amount of work in a given period of time. And let's say that you were to go up that set of stairs with that can of Coke, and you were to do that in 1 second. Well, the amount of work we have is going to be 12 joules, and the amount of time is going to be 1 second. And so the power of that is going to be 12 watts, or W-A-T-T-S, or watts is going to be the amount of power that we have. If you were to do that slower, so let's say we were to do that in 10 seconds, then the amount of watts would drop from 12 watts to 1.2 watts. So that's really not that much power. And so the amount of power that we're actually used to dealing with here in the US is horsepower. And so horsepower is measured it measures the amount of work that we can do in a given period of time. We use it in engines, for example. And so the conversion is 1 horsepower is roughly 746 watts. And so let's go back to that problem. If we're able to move a can of Coke to the top of the stairs in 1 second, we say that that's 12 watts. So if we convert that to horsepower, then we are a 0.004 horsepower machine. So that's not a very powerful machine. Now, the one thing that you should realize is not only are we moving that can of Coke to the top of the stairs, but we're also moving our weight, our whole body to the top of the stairs. And so maybe we're a little more powerful than we think.
He was a major. You probably have heard the words watt and kilowatt. Did you know that the watt is named for James Watt? He was a major contributor to the development of the steam engine. In this unit, you will learn the definition of power, which can be measured in watts. We have seen that forces can do work. Sometimes we are interested in the rate at which work is being done. The car is doing the same amount of work as the donkey, only it is doing it faster, or in other words, it is doing work at a higher rate. The rate at which work is performed is called the power. It is equal to the work divided by the time over which it was performed. The unit of power is the watt, which is equal to 1 joule per second. A kilowatt is 1,000 watts, while a megawatt is 1,000,000 watts. Work can be expressed in terms of power and time. A device consuming 1 kilowatt of power running for 1 hour uses 1 kilowatt hour of energy. A person lifts a weight of 200 newtons to a height of 1.2 meters in 2 seconds. Approximately how much mechanical power is used in lifting the box? Correct. The block is moving at a constant velocity and constant force is being applied to it. The force vector is parallel to the velocity vector. In this case, we can compute the power from the force and the velocity. The power is equal to the force times the velocity. The kinetic energy of flowing water from a small reservoir is used by the water wheel as a source of power. In this simulation, you can control the rate at which the water flows into the wheel, which determines the flow speed of the water and the power output. Once you have achieved the desired power level, you can compute the total amount of energy that can be extracted from the reservoir. Adjust the mass flow rate of the water until the power output is 2,500 watts. The mass flow rate and the total amount of water in the reservoir will be given when you have the correct power output. From this information and the power output of 2,500 watts, you will compute the total work that can be done by the water wheel from all the water in the reservoir. Enter a value for the mass flow rate and click on Run Simulation. The power level is too low. Try again. The power level is too high. Try again. The power level is too high. Try again. The power level is too low. Try. The power level is too low. Try again. The power level is too low. You have found the correct mass flow rate to achieve a power level of 2,500 watts. The reservoir contains 1.20 times 10 to the 8 kilograms of water. Compute the time it will take to drain the reservoir at that rate, and from this, compute the total work that can be done by the water wheel if the reservoir is drained completely. Assume the power level remains constant as the reservoir drains. Good job! Your answer for the total work is correct. Click on the
In physics, we often define quantities, like velocity was defined to be delta x over delta t, or kinetic energy, it's 1/2 mv squared. We make these definitions not just to randomly combine symbols, but because they have physical significance. Energy, kinetic energy, is a quantity which teaches us something about how systems behave. It's got physical meaning. So I'm going to define a new combination of symbols. Right now, it's just a definition. Momentum, it's got a name, and it's given the symbol P, and it's defined to be mass times velocity. So you take an object, and you can define its momentum. I don't know why we use the symbol P, momentum. No, I just think we didn't want to call it M because we're already using the symbol M. It's a useful quantity, but it's not obvious when you look at the equation. Why would this be useful? If you stare at it and think about it a little bit, you can sort of get some sense, a physical sense for what momentum is. If you take an object and you toss it around, this thing has some oomph to it. It's traveling, it hits my hand. Now, what do I mean by oomph? It's a feeling that I've got. Is oomph velocity? Certainly when it's going faster, it's got more oomph. But it's not just velocity, because if I take a little light object and toss it around, even at high velocities, it doesn't have as much oomph as the heavy one. So mass times velocity certainly seems to carry some physical insights with it. We can see another hint about why momentum is a useful physical quantity by thinking about Newton's second law, the center pin of dynamics and understanding how things move. Why? F equals ma. Force equals mass times acceleration. And acceleration is defined to be derivative of velocity with respect to time. dv dt, change in velocity with time. This is Newton's law the way we've been writing it. The way Newton himself wrote it was sliding the m inside the derivative. As long as you have an object with a definite mass, you're free to do so. And what you get then is derivative of mv with time. It's the same equation. And mv, there it is, momentum. Force is dp dt. That is, in fact, the way Isaac Newton thought about the second law. And it's correct. We will discover that when mass is changing, like with a rocket that's ejecting mass, this is the form of Newton's second law that you really want to use. So we've actually gotten to a more fundamental law of physics by introducing this idea of momentum. And, you know, momentum is a property of an object. If you know the velocity and the mass, you know the momentum, and then it's the change in that property with time that tells you about forces.
In this video, we're going to relate tangential and rotational velocity. We're going to begin with a simple demonstration. On the tire, there are two letter E's that are the exact same size, but one of the E's is located at a point near the axis of rotation, whereas the other point is located on the rim, a point that is farther away from the axis of rotation. What you should notice is that the E that is near the axis of rotation is easily recognizable as the letter E, but the E near the rim is blurred. In this video, we're going to talk about why that is. There are two ways to describe the motion of a rotating object. You can talk about the object's rotational velocity, which is how fast the object rotates through a given angle in a given period of time. Now we write that as omega, which is the object's rotational velocity, and that equals the change in the angle, usually expressed in units of radians, divided by the time it takes for that object to rotate through this angle. The other way we can describe the motion of a rotating object is to talk about the object's tangential velocity, which is the velocity of a point on the rotating object. And we write that as a v with a subscript t indicating it's the tangential velocity, and that's going to equal the distance that a point on that rotating object travels through divided by the time it takes for that rotating point to travel through that distance. Now in this video, we're going to talk about the object's rotational velocity, and we're going to talk about the object's tangential velocity, and then we're going to show the relationship between the two quantities. Now the first thing we're going to do is we're going to talk about the object's rotational velocity, which is often called the object's angular velocity, which is again how fast this object rotates through a given angle in a given period of time. Now we said that we can write the object's rotational velocity as the change in the object's angle divided by the time it takes for the object to rotate through this angle. Now as an example, let's suppose this object rotates through some angle. In this case, let's say that the angle through which the object rotates is 45 degrees. Which we can later show that this works out to be pi over 4 radians. If the time it takes for this object to rotate through this angle, this pi over 4 radians, is 2 seconds, then we can calculate the object's angular velocity. And to do that, we'd say that the angle through which this object rotates is pi over 4 radians, sometimes just written as rads, divided by the time it takes to rotate through that angle, which is 2 seconds, and that equals pi over 4 divided by 2, which works out to be 0.39 radians per second. And that's the angular velocity of this object. Now something I'd like to point out is the angular velocity at this point and the angular velocity at this point are identical. Both of these points are rotating through the same angle in the same period of time. And that's true of any point on a rigidly rotating object. So any point on a rigidly rotating object, whether it's this point or this point or this point over here, will all have the same angular velocity because each one of those points is going to rotate through the same angle in the same period of time. Now in the last part of this video, we're going to talk about the tangential velocity of a rotating object. Now the tangential velocity of an object increases the farther you are from the axis of rotation. And that's because a point that is far from the axis of rotation has to travel through a greater distance than a point that is closer to the axis of rotation, even though these 2 points are rotating at the exact same rate. That is, each one of these points has the exact same angular velocity. They're rotating through the same angle in the same amount of time. But since this point way out here has to travel through a greater distance as this wheel is rotating than a point that is closer to the axis of rotation, this point is going to have to travel faster because it has to cover a greater distance in the same amount of time. Now in the last part of this video, we're going to figure out how to calculate the tangential velocity of a point on a rigidly rotating object. And to do that, we're going to use the arc length formula for a circular object. Now I prefer to write this as delta theta, the angle over which we're considering the length of arc, times the radius, and that's going to equal the distance, the arc length. And to give you an idea of what I'm really calculating, the arc length is this length, this distance between these 2 points, and delta theta is the angle between these 2 lines, these 2 green lines. So one way I want you to think about this is, this is the distance through which a point on the wheel rotates, this is the angle through which this wheel is rotating, and this is the distance from the axis of rotation. Let's just work with delta, which is the distance a particular point on the rotating object travels, and again that's going to equal the radius, which is the point that's going to change, times the angle through which this object rotates. Now the time it takes for this point right here to rotate through this distance is going to be the same amount of time it takes to change that angle. And so we can write that as the time it takes to rotate through this angle is going to equal the time it takes for this point right here to travel through this arc, through this distance. Now one of the things I'm hoping that you see is that this relationship here, this delta s, the change in distance divided by the change in time, is really the definition of velocity. And since this object's rotating, we call this the tangential velocity. And the other thing I'm hoping that you see is this quantity right here, this change in angle divided by the time it takes to rotate through that angle, that's really the object's angular velocity. And so we can write the tangential velocity of this object as v subscript t for the tangential velocity equals the radius, the distance from the axis of rotation, times the object's angular velocity or angular speed. And this relationship will tell us how to calculate the tangential velocity at a particular point on the rotating object. Now the last calculation we're going to perform is to figure out the tangential velocity at what we'll call point A, which is the point closest to the axis of rotation, and then we'll figure out the tangential velocity of point B, which is the point farthest away from the axis of rotation. Now for simplicity, we'll call the distance between point A and the axis of rotation, we'll say that that's exactly equal to 1 centimeter. And then we'll say point B, the distance between the axis of rotation and point B, let's say that that's 30 centimeters. Now one of the things that you should remember is that the angular velocity at point A is equal to the angular velocity at point B. And we calculated that velocity in the first part of this video. And we figured that out to be 0.39 radians or rads per second. And so now what we're going to do is we're going to calculate the tangential velocity at each one of these points. So we'll calculate the tangential velocity at point A, which equals the radius at point A, the distance between the axis of rotation and the point A, times the angular velocity at point A. And now this will work out to be 1 centimeter times the angular velocity, which is 0.39 radians per second. And now remember, when you multiply a linear length, in this case a centimeter, times a radian goes away because what a radian really is the ratio of 2 lengths. And so when you multiply 1 centimeter times 0.39 radians per second, you get 0.39 centimeters per second. And that's the velocity, the tangential velocity at point A. Now to calculate the tangential velocity at point B, we'd say that the tangential velocity at point B equals the distance between the axis of rotation and point B times the angular velocity at point B. And in this case, this will work out to be 30 centimeters times 0.39 radians per second. And again, a centimeter times a radian is going to be a centimeter, so 30 centimeters times 0.39 radians per second works out to be 11.78 centimeters per second. So you can see the tangential velocity at a point far away from the axis of rotation is going to be much greater than the tangential velocity at a point close to the axis of rotation.
Let's look at the physics of a playground seesaw. We show the fulcrum with the triangular-shaped support. It's the point about which rotation takes place. A little girl sits at one end of the seesaw, and her boyfriend sits at the other end. Both the girl and the boy have equal weights. We label the forces involved, mg for each kid, and the normal n, the combined weight of the kids acting up at the fulcrum. The forces balance, and we see that the sum of the forces equals 0, the equilibrium rule in action. The kids are able to rock the seesaw up and down by leaning forward and backward in a way slightly shifting their weights. Kids do this all the time. But suppose one of the kids moves closer to the fulcrum. The system is no longer balanced. The girl soon rotates onto the ground, not shown here. For balance, a heavier kid needs to sit where the first boy sat. Then his weight multiplied by his closer distance to the fulcrum will equal her weight multiplied by her distance to the fulcrum. This brings us to a second requirement for mechanical equilibrium, that the sum of the torques on a system also equals 0, where Greek letter tau stands for torque. Equal and opposite torques can produce mechanical equilibrium. Let's drop in on one of my early City College of San Francisco conceptual physics classes and see this physics, not with a seesaw, but with a classroom meter stick.
Look at seesaws. Right now, I have my pivot point, the center of gravity. So what do we find? No rotation. It's not exactly centered. You get the idea, though. Put a weight over here. What happened? Wow. Put another weight over here. Now I'm talking about something you're all familiar with. Isn't that right? If these weights are the same, up and down, and this distance and this distance are the same, then we say the amount of torque that's tending to rotate it this way is just counteracted by what? An amount of torque rotating this way. And if those torques are the same, then I'll have no net torque, I'll have no rotation, if it's not rotating to begin with. And there we are. Isn't that neat? Now you know what's going to happen if I move this one in. I still have the same force acting over here, but I don't have the same torque. That's because my distance is less. And now it goes like that, okay? But I could have something like this. I could have playing with another partner. Let's suppose I could get something like this. You see, you don't have to have equal people, equal mass people playing on the same seesaw. Can you see that? Now, when it comes to balance, when it does, true or false, this weight multiplied by this distance will be exactly equal to this weight multiplied by this distance. Check the neighbor. Anyone say false? Okay.
Let's go back to our seesaw. As we've seen, kids can balance on a seesaw even if they have different weights. Whether they realize it or not, they position themselves so that the sum of the torques cancel to 0. Their torques will be equal and opposite. That is, the torque produced by the girl on the seesaw tends to rotate it counterclockwise, while the torque produced by the boy tends to rotate it clockwise. The two rotational tendencies cancel out. The torques are balanced. Here's something interesting. Even if the girl hangs below her end of the seesaw, balance remains. Why? Because although she's farther away from the fulcrum, her lever arm hasn't changed. The lever arm is the perpendicular distance from the fulcrum to the line of action of the force she exerts on the seesaw. We show the line of action with this purple dashed line. This imaginary line coincides with her weight vector and extends from far above the girl to the center of the earth. The distance between the left end of the seesaw and the fulcrum is the lever arm. always at 90 degrees to the line of action. Recall our treatment of a wrench in our previous screencast, where we defined the lever arm as the perpendicular distance between the line of action of a force and the pivot point. Getting back to our seesaw, we assume that the girl sits 3 meters from the fulcrum, the lever arm distance. Here she dangles 4 meters below the end of the seesaw. What's her physical distance from the fulcrum? That's right, 5 meters. Never mind the 5-meter distance. Her lever arm, as said, is 3 meters, just as it was before she decided to play around.
Simple harmonic motion, like the motion of a mass at the end of an ideal spring, back and forth, very regular motion. We can draw a picture, a qualitative picture of position as a function of time. It's going from positive displacement away from equilibrium to negative displacement, back and forth. We've even been able to write down a formula, although I really just wrote it down. I didn't derive it or explain where it came from. It just seems plausible that this function could be described by a cosine function with amplitude A. I would certainly like to know where this comes from, and that's one of the places where we're headed in this tutorial. But before we derive that equation, I think it's worthwhile just describing the motion as thoroughly as we can, and then we'll do the mathematics. Describing the motion is more than just x. Kinematics means you'd like to know what's velocity and what's acceleration as a function of time. So here's my object on a spring. I'm going to define x as the displacement from the equilibrium length of the string. That's this dashed line. And we'll call positive this away. So we start off at rest with the object stretched out. And what's going to happen? Well, it's going to go back and forth. And that's this graph. It starts with positive displacement, then negative, positive, negative. And now think about velocity as a function of time. At this moment, which we're calling t equals to 0, it's at rest. I just let go of it. Its instantaneous velocity is 0. And then what? It's heading towards the origin, so its velocity is negative, building up. It's getting faster and faster, and then it passes the midpoint. And what happens then? All of a sudden, the force is the other way. So the acceleration is that way, and so the velocity is going to be changing. It's going to be increasing in that direction. An arrow which starts off this way, but its change is in the opposite direction, is a velocity that's decreasing. Let me draw you a picture. It's easier just to look at the graph. It started off 0. It's going more and more negative. You're going really fast when you pass through equilibrium. Notice that the 0 point on x and the most negative velocity occur at the same spot. And as soon as you go past equilibrium, you're slowing down. Your speed is decreasing. In other words, your velocity is getting less and less negative. And when do you get to 0 velocity? When you're all the way compressed. When x is at its first minimum, velocity is back to 0 again. And then the cycle goes the other way. Now the velocity is positive and increasing. The velocity curve gets bigger and bigger. It's a maximum right at the equilibrium point. When x is equal to 0 and you're passing through that equilibrium spot, that's when you're going the fastest. Because as soon as you go a little bit further, the spring is pulling you back and you're slowing down. So the velocity goes back down to 0. So this is the qualitative description of velocity as a function of time.
Wave motion. Wave motion is a form of disturbance which travels through a medium due to repeated periodic motion of the particles of the medium about their mean positions. Types of waves. Waves can be broadly classified as electromagnetic waves, matter waves, and mechanical waves. Electromagnetic wave is a form of disturbance which does not require any medium for its propagation. For example, light. A matter wave is a form of disturbance associated with moving objects. This forms the basis for mechanical wave is a form of disturbance requiring a material medium for it to propagate and are governed by Newton's laws. Water waves, sound waves, seismic waves, etc. are examples of mechanical waves. Types of mechanical waves. Mechanical waves are classified as longitudinal waves and transverse waves. Longitudinal waves. In a longitudinal wave, the particles of the medium vibrate about their mean positions in the direction of propagation of disturbance. Transverse waves. In a transverse wave, the particles of the medium vibrate about their mean positions in a direction perpendicular to the direction of wave propagation. Characteristics of a transverse wave. Transverse waves propagate only in those media which can sustain shearing stress, such as solids and in strings. They propagate therefore only through solid and not through fluids. Transverse waves travel in form of crests and troughs. The distance between two consecutive crests or troughs is called wavelength. Characteristics of a longitudinal wave. Longitudinal waves can travel through solids, liquids and gases as they possess volume elasticity. Longitudinal waves travel in the form of compressions and rarefactions. The distance between two consecutive compressions or rarefactions is equal to the wavelength of the wave. Speed of a wave. V is equal to F into lambda, where V is velocity of any type of wave, F the frequency of the wave, and lambda the wavelength. Speed of a transverse wave. Speed of transverse waves through solids is given by the equation V is equal to root of eta by rho, where eta is modulus of rigidity, rho the density of solid. Speed of transverse waves through a stretched string is given by the relation V is equal to root of T by m, where V is the velocity of transverse wave, T the tension along the string, m the linear mass density. Speed of longitudinal waves. Speed of longitudinal waves in a medium is given by the equation V is equal to root of B by rho, where B is the bulk modulus. This shows that the speed of propagation of longitudinal waves depends only on the bulk modulus and the density of the medium. Newton's formula. Vs is equal to square root of P by rho gives the speed of a longitudinal wave in an ideal gas, where P is the pressure of the gas when the changes in density, rho, takes place under isothermal conditions. Speed of sound or Laplace correction. Laplace pointed out that the pressure variations in the propagation of sound waves are so fast that the temperature does not remain constant and therefore the variations are adiabatic. Vs is equal to square root of gamma p by rho is the modification of Newton's formula and is referred to as the Laplace correction, where gamma is the ratio of two specific heats of gas. Progressive wave motion. A wave which travels continuously in a medium in the same direction without any change in its amplitude is known as the progressive wave. A progressive wave may be transverse or longitudinal. For a wave propagating along x-axis, the equation is y equals a sine omega t minus k into x, where a is amplitude of vibrating particle, omega its angular frequency, k the propagation constant equal to 2 pi by x, x the distance traveled by the wave, and omega t minus k into x is the phase of the wave. The principle of superposition. This principle states that when two or more waves move in a linear medium, the resultant wave at any point equals the algebraic sum of all the displacements caused by the individual waves. Interference. Interference refers to what happens when two waves pass through the same region of space at the same time. It is an example of superposition principle. Waves can interfere constructively, destructively, or partially destructively. Standing waves. Whenever two progressive waves of same amplitude and wavelength travel with the same speed through a medium in opposite direction and superpose on each other, they give rise to standing waves. Standing waves related terms. Node. Node is the point of destructive interference where the chord remains still at all times. Antinode. The point of constructive interference where the end oscillates with maximum amplitude. Natural frequency or resonant frequency. The frequency at which standing wave is produced is called the natural frequency or resonant frequency. Doppler effect. Doppler effect gives the apparent change in frequency or wavelength of sound due to relative motion between source and the listener. The apparent frequency is given by the equation F1 is equal to V plus or minus VO divided by V plus or minus VSO into F, where F1 is the apparent frequency of sound, F the actual frequency of sound, V is the velocity of sound, and VO velocity of observer, VSO the velocity of source.